Any questions?
Okay, that's true, right? That's true, right?
Okay, so stop worrying, pay attention. We're talking about procedure calls.
This is really these are pretty chill.
So for example, in some procedure, we have some code that calls procedure, we'll call it B,
Just like dumb mistakes.
2 parameters. And here's B. So B has 4 variables, 2 arguments, 2 local variables. The scope of these variables is everything inside the squiggle brackets of B. That's where the variables can be accessed. The lifetime of the variables will start at runtime dynamically when this procedure is called, when the procedure is activated, and it goes all the way until this procedure returns. And the procedure may call other procedures, so the lifetime of the variable extends past just what's inside of the squiggle bracket. So in this case, maybe say L0 equals A0, it doesn't matter if it's here, L1 is A1, then we call some other procedure C, and eventually the procedure returns. This is the example that we're going to be working with, but I'm just going to extend the example slightly for what we'll look at a little bit later today, which is a return value. Optional, sometimes you have them, sometimes you don't. Let's say we're going to return something. Something arbitrary. So what we're going to look at today is the code the compiler generates to do all this stuff. And you'll remember from last time that these local variables that are allocated dynamically in arguments are stored on runtime stacks. So we'll look at here's the stack pointer, which is R5. Arbitrarily chose that. And while we're executing in foo, R5 points to the activation frame for B. And when foo calls B, a change has to occur. That's what we're going to look at here. Allocate an activation frame for B. And this is where these variables L0 and L1 reside, also A0 and A1. Also, perhaps some register values that foo wants to be able to access after the procedure returns, and also the same return address. So we'll look at all of those things just to beat them. All right? And then, so this thing is called the activation frame for B. When B finally returns, R5 moves here. In the meantime, while it's here, you will see that B is going to call C. So that will create a new activation frame. And it always goes like this. And the current executing procedure is always the one that R5 points at. Everything below that on the stack are allocated activation frames. Everything above it is free memory on the stack that's available to allocate new activation frames. So we looked at last time, so there's 3 questions on this slide. You can see the first 2. The first one we looked at last time, which is, the question was, why is it that in C and in many languages, local variables don't get a default value? It's also true in Java. Now, global variables in C, if you just say int G, you don't have to say equals 0, it will be equal to 0. But L has an arbitrary value because it's a local variable. And so what was the reason for that? Yes. Right, very good answer. So the difference here is that giving G an initial value can be done statically, because there's just one location for G, and the compiler ensures that, or the operating system actually part of memory where G is already has a 0 before the program starts. So there's no code that needs to execute to make G equal 0. But on the other hand, L is dynamically allocated, and so it's going to be, in memory here that might have stored something else. Now this is the activation frame for B, not for food, but same idea. And so, in order to make sure that it would be 0, the compiler would have to generate code to set it to 0. That code would have to execute. So that would add runtime overhead. So C won't do that. Okay. Then we also saw on the right-hand side here is that you can actually, depending on the sequence of calls that occur, you can know what L is. So if foo and goo both have a local variable in the same position in their activation frame, and you call goo and then foo, and goo puts a number there. So what happened here was that R5 pointed here, there was a call to goo, it put a 3 at offset 0, and then it returned, and that's still there. It's in the free part of the stack now, but the number's still there. And then you call foo, and it doesn't initialize L. The 3 is still there, so if you printed out the value, all you see is 3. Does that make sense? Questions about that? Okay. Now you wouldn't depend upon that. You should consider that to be undefined. But you can, if you understand how the stack works, you should be able to understand why that happens. Questions? Okay. So here's another question. So there's, as I said, there's a question after this. Discuss this with each other. What code does the compiler generate for the very last statement? Do you think? Discuss. Talk to each other. What is that statement? B equals 0. Does anybody have an answer? There's like one really easy answer and then one like head scratching answer. The easy answer is what? Nothing. There's no reason for the compiler to generate any code for B equals 0, because B is about to go out of scope. Its lifetime, its lifetime is about to end. So the compiler, and in fact you're going to see this in a lot of code, is that it may not actually allocate local variables at all. If the procedure is small, it might just use a register to store the value of B. And in some sense, sometimes, local variables are just like temporary things. They just exist while that procedure is running, and maybe you don't need to save it in memory at all, unlike a global variable. And certainly in this case, you don't need to, because there's nothing else after this. Okay, so there's no difference in the execution of this program between the program that has that last line and one that doesn't have the last line.
How does it know?
How does what know?
How does the compiler know if the last line's useless or not?
How does the compiler know
Like,
which is the last line? The compiler sees this code.
so does it say like if the last line is something that works on a variable that's gonna go out of scope and it's not returned, like don't do anything?
Even if it was returned, it doesn't have to do anything. So what you're asking is, how does the compiler know? And the key thing here is that this is a local variable. The compiler knows that, right? It knows the type of variable, it knows where the variable is allocated. And it also knows that there's no statements after it. So everything the compiler needs to know is very easy for it to know. Just like when you look at it, you can see that B's never used again. B's assigned a value, and the program never reads the value of B. And everything that you're using to process that is information that's easily available to the compiler.
If we had a return type, like we had to return B, we would do
No, so this is a good question. So if it was this, and then this, Now, the situation has changed now because the program is using B, but the compiler might just very well put the number 0 into a register and use that as the return value. It may complicate B. I'm not saying it doesn't. I'm just saying in this case, in particular, it doesn't have to. And the reason I'm mentioning that is you're going to see code where there's local variables, but they don't seem to be stored in memory at all. And that makes reading assembly code sometimes a little trickier. Right? Does that make sense? Okay. So if you don't have to do it, you don't have to do it. But what if you did? We now have a problem. We know this is in an activation frame. And we know B is located after A. And we know that in order to store 0 into that location, we're going to store 0, which is an R0, into memory, and we need to know its address, and we know that the address is going to be some constant added to R5, which is the base address of the activation frame. And so what's the problem?
The array is of an arbitrary size.
The array is not, the size of the array is static. So this is kind of weird. And I'm going to mention, you don't need to know this, what this trick is that the compiler uses. But I don't want you to think that that isn't possible. And it doesn't change the fact that this is here. So if you think about what this thing is, can you do this in the global scope? Can I, in the global scope, can I say A bracket n, where n is a variable? No, because if you declare a variable like this in the global scope, this is statically allocated. That must be a constant. But when you do this in local scope, it's because it's being allocated, the whole thing's dynamic. It's sort of a shorthand for this. And then allocating n things. And that, in fact, is how that array is allocated. So it actually looks like this. And R5 strangely points here. So it actually doesn't point to the top of that activation frame. And the compiler will handle this okay, but it puts the next one, it's going to know that there's something hidden on it. But it's always going to be the case that there is a static offset to every variable, even if it looks like one of these variables has dynamic size, because if it does, it's not going to be allocated. Because the pointer is static size. So this 0. And in many instruction sets, there are actually 2 registers that are used to point at the stack. One that points here, in fact, it sort of points in the middle of the activation tree, and one that points here. Also, you don't need to know this, but you hear the term frame pointer and stack pointer. The frame pointer is something that will always point at the static offset within the frame, and the stack pointer always points to the top. Not necessary to have 2, we can do it this way with just 1. So long as we position the stack pointer in a way that we always have static offsets to all the variables. Okay. Questions about that?
So if we want to access like A of 5, would we go up?
Oh, so how do you access A sub 5? It's at the code that the compiler generates is the same code as it does for a dynamic array.
Yeah. Okay, so
It loads the base address. The base address is A. And then it uses that as the base in a second. So even though it looks sort of like this is a static array, the code the compiler generates would be one load to load the value of A from the fixed position on the stack. And now it just has a pointer somewhere. And then that goes into the base address of the array access. It's just like a star. Star
In that sense, then would it also need to load A because it treats A as a pointer as
A. Yeah,
well?
it has to load it.
So in this case, I'm trying to just understand the difference between like this and when we can just take the address of A and like add like integer size chunks. Like, well, why is this seems to be treated differently, right?
It is, because that's not a constant. If you have a constant, then it looks like I drew originally. So if this was
Yeah.
A sub 5, then it looks like this.
And the difference is that it's.
So let me answer, okay. And B has a static offset, and all these things fit. But when the compiler doesn't know the size of the array, it reverts to this form, which is just like this. So even though for local variables you can write something like this, but it's actually that. And this array is not allocated, like if you do this, most likely you're then going to allocate the actual array from where? You can say malloc, right? Allocate it from the heap. You had this, you're probably going to say this. When you do this, you don't have to do the malloc. I mean, this array is allocated by the procedure call, and it's not stored in the heap, it's stored in the stack. But in terms of accessing it, it's exactly the same as this. If that is correct.
If you return something that's, stored on the stack in the previous procedure,
Am I straight now?
does it have to be saved into like?
Let me, I'll come back to this, because I want to now talk about this question, which is relates to what you said. It may not be exactly the same, so ask your question again in just a second. So here I have, well, first of all, any other questions about this thing? So here's another question. So I have a procedure that has a local variable, and this procedure returns the address of the local variable. Is that okay? Is it not okay? Give a name to that problem. Discuss that. Discuss it. Okay, please. All right, who thinks it's a problem? Who knows the name of the problem?
Dangling pointer.
Dangling pointer, very good, thank you. Why is it a dangling pointer? Well, when you return, that variable L is now in the unallocated part of the stack, just like if you said free. But the caller, which is now executing on this, in this activation frame, has a pointer to it. And if it accesses that, then it's accessing memory that's unallocated. Now, it's actually a bit different than a regular dangling pointer, because if it just does that, then, and it doesn't call any other procedures, it's going to be okay, actually. But as soon as it calls another procedure, then that procedure is going to write over top of this memory, possibly. And at that point, the dangling pointer will have sort of other things in it, related to the subsequent procedure call. But you never actually have the problem. The worst problem of dangling pointers is when you use a dangling pointer to change memory, and there was another object that was allocated in that location, and you're corrupting that object. And that actually can never happen here, because you'll always be pointing above on the stack. Unless, of course, you pass it again. Okay. So that's a dangling pointer. Questions about that? What about this one? Who thinks there's something wrong with that? Let's discuss it. Okay, so we know a program that calls malloc to allocate an object and never calls free to release the memory where that object is stored has a bug. That's called what? A memory leak. Does this program have a memory leak? Yes. Is it guaranteed it has a memory leak? Yes, because when that procedure returns the variable L, which is the only pointer to the object, goes away. But the object itself doesn't go away. Right? There's still this reserved memory in the Okay, now, your question, did I touch on it? It was, oh, gee, I'm so sorry. So it was about if you return something to something on the stack. That's what
Oh, yes, you know, like, if we have like an array that you allocated on the stack.
Yeah.
Say, like we said earlier, you put that, then does it just like save that memory in the stack?
No, so you're back in this example here where when you know you return from this and you're down here again. What is it legal to return? Well, you can return the value of anything in the array because you're copying values from here to somewhere else. But you can't return the address of anything. So you can't return the address of any. You know, this array is gone when the procedure returns, just like the other variables are. It's the same as L. It's the same as this. Does that make sense?
But it would be allowed, it's just not.
No, well, what do you mean it's allowed?
Like,
You're allowed to write buggy code. Yes, yeah, it's allowed. So maybe what you mean by allowed is there a static error? And there's a lot of bugs in C, of course, that there aren't static errors for. The compiler is very, very forgiving about the way you use pointers, unfortunately. Yeah, so you can return. This code will not generate a static error, and neither will that one, but they're both serious bugs.
is that second case of the memory avoided in Java by the constructor?
Yeah, so in a garbage collected language, that you don't ever say free, and at this point that object becomes unreachable. There's no more pointers to it, so it would eventually be selected. Yeah. Other questions? Okay, so now let's turn to what the compiler does to implement this call. And what we know from what we were talking about earlier today, Monday, that there's a set of things that have to happen. So one thing that has to happen is the control flow. So let me just draw out the control flow, which is, I want to move this down. So the control flow is a jump to be preceded by getting the return address into R6. And then at the bottom of B, the very last thing is going to be a jump, R6. And so that's the control flow part. Now, in addition to that, we need to allocate the activation frame on the call, deallocate it on the return, and also copy the numbers 1 and 2 into the initial values of the two arguments A and B. That activation frame will look like this. So, we have to allocate this memory. We have to have something that will subtract some number. And what is that number? How big is this activation frame? That's 4 bytes long. 4, 8, 12, 16, 20 bytes, right? So somewhere along here, we have to subtract 20 from R5, and somewhere along here, coming back, we have to add 20. And then in addition to that, at these two positions, which will be offset 0, 4, 8, 12, and 16, we need to store a 1 and a 2.
Is that activation frame always 20 bytes, regardless of the code C and D?
Yeah.
Or will it change because
The size of an activation frame is determined by the things that are stored in it. And what's stored in it? the compiler knows the size of all of those things statically, and it knows what they are. So it's the local variables in the argument. So here there's 4 of those, and the types happen to be in, so they're all 4 bytes long. So that's 20, that's 16. And then the return address, which is a pointer. Now that actually, in C would be 8 bytes long, but if we're doing an assembly language, as we have here, it's just 4 bytes long. And then there may be some other things for save registers, so the compiler will know how much that is. So it could be a bit more than this if it's saving some register values, but it'll always know what it is. And it's independent of anything that happens in the program after this. It can statically determine that just by looking at read. Okay. Does that make sense? Okay, so we think about this now. So we have to allocate, there's basically 3 things. Allocate, deallocate, and save the arguments. And we can add code here, and we can also add code here. So we can put, we could allocate the activation frame right here, for example, and deallocate it here. Or we can allocate the frame here and deallocate it here, either way. Where is it in this code, here or here, that we know the value of those 2 arguments? 1 and 2. You know that here. When the code is executing here, the compiler looks at this. Does it know that A0 is 1 and A1 is 2? No. Why not? Well, that's not the only call to B. You might call B some other place in your program with different numbers. So the initial value of the arguments is not determined by the procedure, which we're going to call the call E. It's determined by the particular call, the call verb. Does this make sense? So a part of this business of allocating the activation frame has to happen here. Now we actually could do all of it here, but then we'd have a bunch of code that we have here that at every procedure call we'd have that code. So let's say there's 1,000 places we call B. Well, I've got a bunch of code that's all exactly the same for every call to B. So rather than replicating that at every place, we'll put that part here. So this ends up with this kind of complicated implementation where we're going to have some parts of the allocation of the frame as part of the call, because we absolutely have to do that, the argument part. And we're going to call that the caller, this is the caller to be prologue. Okay, and we'll come to this in a second. And then everything else, it's always going to be the same for every call to be. We'll put over here at the very beginning, and we'll call that the call E prologue. And then when we get to the end, there's a sort of reverse thing we have to do. Allocate, deallocate. You'll see in a minute. Save the return address, restore the return address. We'll put that here as well. So that's the call E epilogue. And then finally, we have to do the reverse of what we do here. And we'll call that the caller epilogue. So there are these 4 parts, as you can see on the screen here, that the compiler puts code in. Does this make sense? We've got a part here, and a part here. A part here, and a part here. Okay. So I want you now to talk to each other and write out what is the code for this call, B1, 2. What is the code the compiler generates for the call E prologue? Just talk to each other for a minute. Now, I don't want to talk to you. All right, so don't now give me the code, but tell me, describe what we have to do. What's one thing we have to do? I have to change, I have to move the stack to make space for the arguments. So right now, here we are. Here's our font. And the suggestion here is let's move the stack pointer just enough so I have room for the two arguments. So how would I do that?
R5 minus 8.
I have to subtract 8 from R5. So here's how I would do that. Load $-8, say R0, and add R0 to R5. That, when it executes, accomplishes this. It's allocated a part of the activation frame for B. And this part actually has a name. It's called the argument build area, but you don't need to know that. And what's the other thing I need to do? I have to store 0 here and 1 here. Right? So that's, what is it? 1 here and 2 here. So I do this. I'm going to put 1 into R0 and then store R0 at the offset for A0 from the current stack pointer, which is what? Stack pointer is pointing here at 0. 1, 2, R0, and store R0 down into 4 from R5. So this is A1 equals 2. This is A1 equals 1. And then I make the call. Something's happened. And I come back. And if I want to undo what I did here, and just assuming the stack pointer is here now, move it back here, what do I need to do? Here. To get the stack pointer from here back to here, I have to add 8. Okay? So that's the template for the call. All of this is the procedure call. This procedure call has these sort of 3 parts. It has the part that allocates the part of the activation frame for the caller, the callee, that stores the arguments. And then it copies the values of the arguments onto the stack at those locations. Then it computes the return address and jumps to that procedure. Now the return address, of course, is going to be pointing at that line of code. And when the procedure returns and you come back here, it deallocates that part of the activation frame that it allocated up to.
Is that for construction supposed to be A0 because
Fourth instruction. 1, 2, 3, 4.
yeah.
You comment.
There you go. Oh.
Yeah. Any questions about that part? Okay, so now we're over here. We have more stuff to do, right? Because the activation frame must have this in it. So this part now has been allocated. And R5, when we get there, this is what the stack looks like. At the very beginning of B, that's what the stack looks like. And we need to add the local variables and the saved return address. Now, just a pause for a moment. What is that saved return address? Why do we have that? In this picture at this point, where is the return address? I'm executing at the very beginning of B. The return address is the address of that instruction. It's where B is going to jump back to at the very end of the procedure. Where is the return address right now? Right here. R6. In R6. Why do I have to save it onto the stack?
If that function calls another function, then it would put it would overwrite the.
Right, so I'm gonna reuse R6 when B, for example, calls C. And so I need to save R6 onto the stack, and so that's what this is. We need to have this be a pointer to that line, which is the value of R6 when we start, okay? So I need to do these three things. How do I do that? Well, it's just kind of like this, right? So I have to now subtract something else from R5. So how big is that part that we have to allocate the rest of the frame? 16. This is 4 bytes long. Cool. So load $12, $0, add R0, R5. That will accomplish this. Now, there are instructions that access the local variables and arguments, but that's not the prologue. The prologue is just all the stuff that comes before that. So, for the local variables, I don't do anything, I just make space for them. But the return address, I do have to do something. I now have to save R6 into that position. And that position is at offset 0, 4, 8.
When you load 12 into R0.
Oh, it's minus 12.
Okay.
Sorry, thank you. Subtracting. I could probably write that. Oh, no, where is it? Load minus 12. Okay. That's the end of the call E prologue. Now when I get to, so now we'll do all this stuff here, which is just normal code now. That's the body of the procedure. And I get to the end, I'm just about to return. Ignoring the return value for a moment. What do I have to do to undo this? I want you to discuss that with each other. And write the code. So I have to do two things. What are they? Well, so I have to add 12 to the stack pointer. What's the other thing I have to do?
You have to load.
Yeah, I don't know. Anybody?
You have to load the return value from 8 R5 to R6.
Right. I have to restore the stack pointer register to point to what's stored in the stack, because this may have changed. It will actually have changed. It will change right here, because in this call there's going to be a GPC. And R6 at this point is actually pointing to the instructions right after this call. Right? So that will be a load. So it's just reversing this one, 8 from R5 into R6, and then reversing this part, put a 12 into R0. I'm actually going to use R1 for a reason you'll see in a second. And then add R1 to R5. So when the procedure starts executing, it moves the stack pointer up, so now it's allocated the entire activation frame. It saves the return address, then it executes the procedure. When it's all done, it reloads the return address from the stack, and then it shrinks the activation frame back down to where it was at the beginning of this procedure. and then it jumps back to the instruction that is at the return address location, which is right here, and then it removes the rest of the activation frame, and the procedure calls over. Questions about that? Okay, so there's one last thing, which is the return value. So this procedure generates a value that data has to be passed back to this procedure over here. Now, how would you think we might do that? To pass values in this direction, in the call, we put them on the stack. How might we do it here? I want to pass the value back. Well, I could put it on the stack as well. But since there's always only one return address, and if the return address is a number, the convention is to leave that value in a register, and by convention it's register 0 in R, so in x86 that's called register A, that's register 0. For us it's register 0. So you would do, so here I'm going to add these two things. So here's the body, I'm going to load A0 and A1, this is 0, 4, 8, 12, and 16. So load 12 from R5 into R0, load 16 from R5 to register 1, add register 1 to register 0. That's the return value, so when I come here, I'm just going to say, so now, I want to store that in the variable x. So let's say x is a global variable. Okay. So when you're reading assembly code, you'll see, okay, well there's a value that's left in R0, and then it's never accessed again here, but then you access it here right after the call. That's the return value. Okay, so this is complete now. So we have the data, moving the data flow. The argument values are stored on the stack as part of the call. They're then accessed during the call. A value is generated here and is placed in R0, which is available here after the call. We have the control flow part, which is storing the return address in a register here, jumping here, and then saving the return address on the stack here, restoring it from the stack here, and jumping back to that location. And we have the dynamic allocation of the activation frame. Part of it's allocated here, the rest of it's allocated here, part of it's deallocated here, and the rest of it. Does this make sense? You don't have to take a picture of this, I mean, you're welcome to, but it's all in the slides. So let's go through this in the slides now. So, caller prologue in RTL. Well, here, I did 1 and 2 here, and this is 0 and 1. Okay, but subtract 8, that makes this happen. Call lead program prologue, this is in B, subtract 12, and store the return address. That makes this happen. And then at the very end, restore the return address, deallocate that part of the activation frame, minus 12 plus 12, and then back in the call, or add 8, undoing that. So it looks like that. Now, that can be a little intimidating to look at. It's a lot of code. As soon as you introduce one procedure code, it's a lot of code, which is great for writing exam questions, but makes it hard. And so the same thing has to happen here as everything else we've talked about when you're looking at assembly code. There is embedded structure that needs to emerge out. You need to make it explicit. And so you know that every procedure call has got this. This is the call. All of this that's not shaded out is the call in foo to B that we talked about. And this is all the code that I just wrote here, except that I have that is a 1. That's a 2. So you know that there's this part that sets up the activation frame, saves the arguments. There's this part that does the control flow, jumps here, you know, at the beginning of a procedure. There's always gonna be something related to the activation frame. And then you've got the body of the procedure, and at the very end, every procedure you undo what was here. And when you get back, after the call, you have to undo what was here. And so there are these bits of things that once you draw a box around them, you can sort of, you know, treat them separately when you're reading the code. This slide, I'm not going to spend much time on. It just shows you an alternate way that you could do this and indicates why this would be inefficient. So what we could do is save the arguments on the stack here and then allocate the entire activation frame. And what you end up doing in that case is you get this thing on the bottom where you duplicate the arguments. And you have to copy them from one place to another. And so what we've done is just an optimization on the top. We just sort of merge those two parts together so that you only save the arguments once. Now, yes, you had a question a long time ago.